Hello everyone, it's my great honor to give this presentation here. My name is Ziwei Yang from Dalian University of Technology. The topic of my report is Cooperative Game for Multiple Chargers with Dynamic Network Topology. This work is collaboratively by Jing Deng from University of North Carolina at Greensboro and Chi Lin, Ziwei Yang, Yu Sun, Lei Wang, and Guowei Wu from Dalian University of Technology. This is the outline of this work. It is mainly divided into the following 6 parts. The wireless sensor networks have already been used for decades, such as agricultural, industrial, and climate monitoring. However, the limited energy hinders the wireless sensor networks working perpetually. Fortunately, benefiting from the wireless power transfer technology, such as inductive coupling, magnetic resonance coupling, and electromagnetic radiation, the concept of wireless rechargeable sensor networks is proposed, which can solve the energy capacity problem of wireless sensor networks. Supported by the DMPT technology, wireless rechargeable sensor networks (WRSNs) have become an important research topic. This is a diagram of WRSN. It has 3 main components: the basic station, rechargeable sensors, and the mobile charger. The base station is used to collect sensor data and provide energy for mobile chargers. Rechargeable sensors are used to monitor events and environment. Mobile charger is used to replenish energy for these sensors. With these understandings, we make a pioneering attempt to aiming at carefully designing MCs to serve WISNs with dynamic topology through collaborative game theory. When solving the problem, we're facing 3 critical challenges. 1. How to determine the subset of sensors that will cooperate with each other and form a coalition. 2. How to allocate the profit to the sensor within the same coalition. 3. Due to the dynamic feature of the network, how to preserve the optimal coalition structure. The contributions of this paper are summarized below. 1. Through theoretical analysis and simulation verifications, we prove that our scheme can achieve Pareto optimality and ensure the minimum non-charging expenditure ratio. We convert the charging problem into a cost allocation problem among sensors. We propose a profit allocating scheme for each coalition based on the Shapley value. Game theory is a theory of applied mathematics that models and analyzes systems in which each individual tries to find the optimal strategy depending on the choices of others in order to gain success. Generally, the game theory contains 3 basic elements: the players involved in the game, the action strategies that players can perform, and the benefits obtained after executing the strategy. In game theory, Pareto optimally is usually used to optimize research allocation as well as restrict players' behaviors. When reaching the Pareto state, the total profit of all sensors is maximized. In this work, we employ multiple MCs with energy constraint to solve sensors to ensure none of them will run out of energy. As the charger sensors are the main concern for MCs. We aim to minimize the non-charging expenditure ratio of MCs, which is defined as the ratio between MC's total traveling cost (EM) and total energy obtained by sensor (EU). Formally, our problem can be defined as give a number of MCs, how to scaling them to charge sensors so that their overall non-charging expenditure ratio eta is minimized. We formulate this problem as P0. To achieve the goal of question P0, the key lies in how to minimize the total mobile energy consumption of wireless charging hubs. Hence, we convert P0 into P1 with energy constraint. Each sensor with a constant demand of energy is regarded as the customer, and each MC with limited energy capacity works for servicing the demands of the customers. Besides, the total cost for servicing the subset of sensors cannot exceed the MC's capacity. Formally, the transformed problem can be expressed as P1. In our scheme, each sensor is regarded as a player in the game. Collision S is a subset of sensors and its profit is determined by characteristics function Vs. Since players in the cooperative game have the common objective of maximizing the total profit, we can reverse the traveling cost to compute the profit of a collision as Vs. According to equation 17, we note that the more profit the collision S gains, the less energy for serving the sensors in collision S will be consumed for traveling. In our analysis, the optimal collision structure is actually the solution of P1. Therefore, instead of directly solving P1, which has extremely high computational cost, we convert it into a cooperative game among sensors and try to find the optimal collision structure. Thus, P1 can be converted into the following problem, P2. Here, Vs represents the profit of the collision S and A is the set of all possible collision structures. In this paper, we propose a scheme named CGTCS to solve P2, which always guarantees to construct the optimal collision structure when confronting with network dynamics. We propose a CFG algorithm to judge the feasibility of a collision as well as collecting the charging route for it. According to CFG algorithm, for any collision whose size is smaller than EC divided by delta E, when the collision satisfies the tight constraint, CFG algorithm will return a non-empty servicing path. Otherwise, nothing will be returned when a collision is infeasible. According to OCSC algorithm, we can construct the optimal collision structure by the following steps. First, we initialize the optimal collision structure by treating each sensor as a collision. Second, the link matrix is constructed and the weight of this link is computed. Then we interactively construct the optimal collision structure. In our iteration process, we search for the two nearest collisions, which means the weight of the link between them is maximized. Then we merge these two collisions and update the collision structure as well as the link matrix. The iteration repeats until no collisions can be merged. At last, we obtain the optimal collation structure CSC. We allocate the total profit of the collation based on the Shapley value. Formally, for any sensor Ni in the collation S, pi is denoted the allocated profit, which can be computed as pi. Therefore, the Shapley value reflects the average allocation for the player's marginal contribution. Usually, it ensures the uniqueness of the profit allocation. We investigate how to timely update the collation structure to mitigate the influence of such dynamic. According to AOCSU algorithm, the process of updating the collation structure proposed as follows. Whenever a new sensor joins in the new network, it will send a message to the leaders of the current collation structure. For each leader, it will execute CFG algorithm to check the feasibility of the collation after adding the new sensor. If feasible, a welcome message will be sent to the sensor. Otherwise, it will select a victim to remove and add the new sensor. Finally, the sensor gathers the welcome messages from the leaders and selects a collation to join in, which achieves the highest profit. Thus, the collation structure can be updated in a self-organized way. In general, the purpose of the multiple charging schemes is as follows. First, we construct the optimal collation structure. Then, in each collation, a leader is designated who owns all sensors information belonging to that collation. Once the collation topology changes, sensors will adaptively update the collation by computing with the collation leader to maintain optimal collation structure. Since no previous studies have ever applied a cooperative game theory to address the charging scaling problem in WSNs with multiple MCS, we propose three algorithms as baseline for comparison. In this figure, the total traveling cost increases with the number of sensors increasing. Clearly, CGTCS has a minimum total traveling cost. Comparing with MTS, ES, and NSD, CGTCS algorithm reduces the traveling cost by 30.6%, 11%, and 6.63%. After that, we carry out some simulations in small-scale networks to demonstrate the advantages of our scheme. The parameters of simulation are shown in the table. Let's look at the experimental research of large-scale network simulation. Comparing with the other three algorithms, CGTCS has the lowest traveling cost. As the number of sensors increase, the traveling cost the MC increase. Such an increase is due to the extra traveling cost for charging sensors. As the minimum energy required for sensors to keep operational E-min limits the amount of energy delivering to sensors. We observe it decreases as E-min increase. Moreover, the traveling cost CGTCS is always less than MTS algorithm and gains the lowest value among four algorithms. This means our algorithms has an obvious superiority in adapting the variable lifetime of sensors. Figure 7 demonstrates the impact of AOCSU algorithm. In Figure 7, the traveling cost of CGTCS with AOCSU algorithms is less than that without AOCSU algorithm. When applying AOCSU algorithm, the collation structure is always optimal no matter how network topology changes. Finally, we come to the conclusion of this work. In this paper, we proposed a CGTCS scheme to address the charging scaling issue in WSNs with dynamic topology, which mainly included three algorithms: CFG, OCSC, and AOCSU. First, CFG algorithm is used to judge the feasibility of the collision and calculate the service route. Second, we develop an OCSC algorithm to find the optimal collision structure to ensure the minimum total traveling cost. Third, we utilize the Shapley value to allocate the profit for each collision so that the collision is stable, indicating that no sensor will violate this collision. Then an AOCSU algorithm is introduced to update the optimal collision structure to adapt to the dynamic network. Furthermore, we conducted both field experiments and simulations to evaluate the performance of CGTCS. The results reveal that CGTCS outperforms other comparing algorithms by at least 5% and 12% in terms of non-charging expenditure ratio and total traveling cost in dynamic topology. Thanks a lot for working. If you have any problem, please email us. Thanks.